So let's take a look at line integrals. Now let's say we have the integral of some multivariable function f of x, y, ds along a certain curve or a smooth path c, and we're trying to find a way to evaluate this. Well, the formula, let's say we're given also two parametric equations, x of t and y of t, and we're also given the t bounds range from a to b. We can say that the formula is going to be the integral from a to b of f of x of t. So we're basically replacing x with x of t, and we're going to replace y with y of t. So we have f of x of t comma y of t times ds, and so ds is going to be equal to the square root of x prime of t, so we're going to take the derivative of the x equation squared plus the derivative of the y equation squared, so y prime of t squared, and then we have dt on the outside. So basically we're going to take everything and replace it with t. So for number one, let's evaluate the line integral. So we have the integral along c of y times ds, and so c is described by two parametric equations, x equals t squared and y equals t, and the t bounds or t ranges from 0 to 2. So the first thing we would do is start off by replacing everything inside the integral with the parametric equations. So y is obviously equal to t, so we're going to replace y with t. So we have the integral of t times ds. Now remember, ds is going to be equal to the square root of x prime of t squared plus y prime of t squared. So if x is equal to t squared, then x prime of t, or x prime, is going to be equal to 2t, since we're just taking the derivative of the x equation. And so x prime of t squared is going to be 4t squared, and then plus y prime of t squared. So if y prime, or if y equals t, then y prime of t is going to equal 1. So then 1 squared is just 1. So we have square root of 4t squared plus 1, and don't forget we do have dt on the outside. And the t bounds are from 0 to 2, so we're going to put from 0 to 2. So now in order to evaluate this integral, we can just go ahead and use u substitution. So if u is going to equal to 4t squared plus 1, then du, or the derivative, is going to be 8t dt. So then dt, if we isolate, is going to be du over 8t. So if I go ahead and substitute everything back into the integral, we get the integral from 0 to 2 of t times the square root. Remember, we made u equal to 4t squared plus 1, so the square root of u times dt, which once again is du over 8t. So notice the t's will cancel. 1 over 8 can come outside the integral as a constant, so we get 1 over 8 times the integral from 0 to 2 of the square root of u, or I can rewrite it as actually u to the 1/2 du. So now we can use the power rule. So we get 1 over 8, and the integral of u to the 1/2 is going to be 2/3 u to the 3/2, since u is equal to 4t squared plus 1. Or before I do that, I'm just going to go ahead and multiply the two fractions. So 1 over 8 times 2 over 3 is going to be 2 over 24, which is 1 over 12. Now I can go ahead and substitute back in our u of 4t squared plus 1. And then we have that to the 3/2 power. So let's go ahead and evaluate using the t bounds from 0 to 2. So when I plug in 2 for t, we'll get 1 over 12 times, well, 2 squared is 4, 4 times 4 is 16, 16 plus 1 is 17, so 17 to the 3/2 power, minus, when I plug in 0 for t, we get 0 plus 1, which is 1, and 1 to the 3/2 is 1. So that's going to be the final answer. So now for number 2, we have the integral along the curve c of x times y to the 4th ds, and we're given that c is the right half of the circle, x squared plus y squared equals 16. Now notice in this problem we aren't given any parametric equation in terms of t, but the good thing is that we can easily find them. Now the unit circle, if we take for example, is going to be described by the equation x squared plus y squared equals 1, since this equation describes a circle that has the center at the origin and has a radius of 1, which is exactly the unit circle. Now this is good to memorize. The unit circle in parametric form can be written as x equals cosine of t and y equals sine of t. Now in this case, or the equation that is given to us, the radius is equal to 4. Since r squared is 16, so r is going to be 4. Now how could we get from a radius of 1 to a radius of 4? Well, all we have to do is multiply by 4. So if we go ahead and multiply both of these parametric equations by 4, we get x equals 4 cosine t and y equals 4 sine t. So these two parametric equations are going to represent x squared plus y squared equals 16. Now in order to find the bounds of integration, we need to go ahead and graph this circle. So So I go ahead and graph this on an XY plane. Obviously the center is at the origin and the radius is 4. Now it's asking us to calculate only the right half of the circle. So if we do only the right half of the circle, notice the bounds of integration are from negative pi over 2 all the way counterclockwise to positive 90 degrees or positive pi over 2. So we can say the t-bounds range from negative pi over 2 once again to pi over 2. So if I rewrite the integral, we get the integral from the bounds negative pi over 2 to positive pi over 2 of x. Now x is equal to 4 cosine t, so I'll write 4 cosine t times y to the 4th. Now y is going to be 4 sine of t, so the entire thing to the 4th power. Now 4 to the 4th is going to be 256, so 256 sine to the 4th t. And then we have times ds, and remember ds is going to be equal to the square root of x prime of t squared plus y prime of t squared. So if x equals 4 cosine t, then x prime of t, or the derivative, is going to be negative 4 sine of t, and x prime squared, or negative 4 sine t squared, is going to be 16 sine squared of t. Now plus y is going to be equal to 4 sine of t, so y prime is going to be 4 cosine t, and so the derivative squared, 4 cosine t squared, is going to be 16 cosine squared of t. And don't forget we do have dt on the outside. Now I can go ahead and simplify what's under the radical here. So if I factor out a 16, we get sine squared of t plus cosine squared of t. Sine squared plus cosine squared is 1. 1 times 16 is 16, and the square root of 16 is 4. So if I go ahead and multiply all the constants together, we get 4 as we simplify the radical. So 4 times 4 is 16, and 16 times 256 is 4096. Since that is a constant, I can take that outside the integral. So we get 4096 times the integral of cosine t times sine of the 4th t dt. So rewriting the integral, we get the integral from negative pi over 2 to pi over 2 of 4 cosine t times 256 sine of the 4th t times, now we simplified this entire thing down to just 4. So we have times 4 dt. So 4 times 256 times 4, if I use my calculator, is going to be 4096. Since that is a constant, I can take that outside the integral. So we get 4096 times the integral from negative pi over 2 to positive pi over 2 of just cosine t times sine of the 4th t dt. So now in order to evaluate this, I can just use u substitution. So if u is equal to sine of t, then du is going to be cosine t dt. And so if I isolate dt, that is going to equal du over cosine t. Now let's go ahead and substitute everything back into the integral. So we get 4096 times the integral from negative pi over 2 to positive pi over 2 of cosine t times, now I made u equal to sine of t, so we have u to the 4th times dt, which is du over cosine of t. Notice the cosines will cancel, and so we're left with 4096 times the integral of u to the 4th du. And so the integral of u to the 4th is u to the 5th over 5. So we get 4096 times u to the 5th over 5. Now I'm going to go ahead and group these together. So we get 4096 over 5 times u to the 5th. Now u is once again sine of t. So we have sine of t to the 5th. Let's go ahead and evaluate that from the t-bounds, once again from negative pi over 2 to positive pi over 2. And so when I go ahead and evaluate, we get 4096 over 5 times, now sine of pi over 2 is going to be 1, 1 to the 5th is 1, minus sine of negative pi over 2. Sine of negative pi over 2 is going to be negative 1, and negative 1 to the 5th is also negative 1. So minus a negative 1 would mean plus 1. And so we have 2 times 4096, which is going to be 8192 over 5. And that's the final answer. So now for number 3, we have the integral along C of x times y plus ln x dy, and given that C is the arc of the parabola y equals x squared from the points 1, 1 to 3, 9. So realize that instead of ds, we're given dy, and instead of parametric equations, we're given that y equals some function in terms of x, so y equals f of x. So whenever you're given that C is the arc of the parabola, of some function y equals f of x in that form, we're basically trying to find the line integral with respect to arc length. So the formula for this is going to be a little bit easier than the previous problems. Basically, we're going to choose one variable. So in this case, since y is in something in terms of x, we're going to choose x as our variable and put everything in the integral in terms of x. So we're basically going to replace y with x squared, since y is equal to x squared. So we get the integral of x times x squared plus ln of x, and then times dy. Now if y is equal to x squared, then dy, or the derivative, is just going to be equal to 2x dx. So we go ahead and replace that with dy. So we have times 2x dx. And since everything is in terms of x, we have to use x bounds. Now realize that it goes from 1, 1 to 3, 9. So we're just going to take the x coordinates. So we're going to go from the x coordinate of 1 to the x coordinate of 3. So from 1 to 3. So if I simplify it, we get the integral from 1 to 3 of x cubed plus ln x times 2x dx. Now 2 can come outside the integral as a constant, and I'm going to go ahead and distribute over the x. So we get 2 times the integral from 1 to 3 of x to the 4th plus x times ln x dx. Now the integral of x to the 4th is just going to be x to the 5th over 5. But how can we integrate x times the natural log of x? Well, we have to use integration by parts. So I'm going to go ahead and make u equal to ln x, and then dv is going to be x. And I have my plus minus column here. So the first row is going to be positive. The derivative of ln x is going to be 1 over x, and the integral of x is going to be x squared over 2. And the next row is going to be minus. Now if I keep on deriving the u column and keep on integrating the v column, they're basically going to go on forever. So I'm going to stop at the first row that I integrate and derive, and then I'll go ahead and group these together. So we multiply and we get x squared over 2, or 1/2 x squared, times ln x, where you have minus, and then minus the integral of the same row. So we have 1 over x times x squared over 2, which is just going to be 1/2 times x dx. And so the integral of 1/2 x is going to be 1/2 times x squared over 2. So we get 1 to the 4, or 1 over 4 times x squared. And so we have 1/2 x squared times the natural log of x minus what we found for the integral of 1/2 x, which is 1 over 4 x squared. So once again, if we go back up here, the integral of x to the 4th we found to be x to the 5th over 5, and the integral of x ln x we have found to be this entire thing. So I'll go ahead and put that up here. So plus 1/2 x squared ln x minus 1 over 4 x squared. Don't forget we do have a 2 out as a constant. Now I'm actually go ahead and distribute over the 2. So we have 2 over 5 times x to the 5th, and then plus 2 times 1/2 is just 1, so we get x squared ln x, and then minus 2 times 1/4, 1/2 x squared. Let's go ahead and evaluate from the x bounds of 1 to 3. So then when I plug in 3, I should just write that down here. When we plug in 3, we'll get 2/5 times 3 to the 5th. And if I use my calculator, 3 to the 5th is going to be 243 plus 3 squared, 9 times ln of 3, and then minus 1/2 times 3 squared, so then 9/2. Minus, when I plug in 1 for x, so we'll get 2 over 5 times 1 to the 5th, so there's 2/5, plus 1 squared, which is 1, times ln of 1, and then minus 1/2 times 1 squared, which is just 1/2. Now ln of 1 is 0, so that can cancel. And so 243 times 2 is going to be 486, so we get 486 over 5 plus 9 times the natural log of 3 minus 9/2, and then minus 2/5, and then you have a negative and negative, that'll cancel, so positive 1/2. So if I rewrite and simplify, so we get 486 over 5, I'll rewrite that once again, plus 9 times the natural log of 3. Now negative 9/2 plus 1/2 is negative 8/2, which is negative 4, and then we have minus 2 over 5. Now we get 486 over 5 minus 280, or 2 over 5, which is going to be 484 over 5, and then minus, now 4 can be written as 20 over 5, plus 9 times the natural log of 3. So 484 minus 20 is 464, so the final answer is going to be 464 over 5 plus 9 times the natural log of 3. So now for number 4, we have the integral along C of x times y dx plus x minus y dy, and C consists of line segments from 0, 0 to 2, 0, and from 2, 0 to 3, 2. And so notice in this problem, we're not given ds, instead we're given both dx and dy this time. And we're not given a function y equals f of x, instead we're given two line segments from 0, 0 to 0, and from 2, 0 to 3, 2. Now realize that C consists of two line segments. So what we can actually do here is break this up into one line segment and break it up to another line segment. So if we take the integral of the first line segment, so C1, plus the integral of the second line segment, C2, we'll get the integral of both line segments, C. So from 0, 0 to 2, 0, that is going to be line segment 1, and from 2, 0 to 3, 2, that is going to be line segment 2, or C2. Now the first thing we need to do is, since we're not given a function, we need to find parametric equations. And so the formula in order to find those parametric equations is going to be r of t, the vector function, equals 1 minus t times r sub naught plus t times r sub 1. Now r sub naught is going to be the initial point written in component form, and r sub 1 is going to be the terminal point or the end point written in component form. So let's go ahead and first find the vector function for C1, or the first line segment. So r of t is going to equal 1 minus t times r sub naught. Now the initial point is 0, 0, so written in component form, we just write it as 0, 0, plus t times r sub 1 written in component form, which is just going to be 2, 0. So if I go ahead and distribute over the 1 minus t into the vector, we'll obviously just still get 0, 0, and then plus, if I distribute the t, we'll get 2 times t, so 2t, comma, 0 times t, so just 0. Now if I go ahead and add those two vectors together, we get 2t plus 0, which is 2t, comma, and then 0 plus 0, just 0. So that is going to be the vector function r of t. And notice it gives us the x component and the y component, both in terms of t. So x is going to be equal to 2t, and y is going to be equal to 0. Now I forgot to mention this earlier, but whenever we use this exact equation, the t-bounds are always going to be from 0 to 1. So now let's go ahead and set up the integral along the first line segment C1. So the integral along C1, now once again we're going to replace x with the parametric equation, x equals 2t. So we have 2t times y, which is equal to 0, so times 0 times dx. Now if x is 2t, dx is just going to be 2, and then plus x minus y times dy. So we have x is going to be 2t minus y, which is 0, and then times dy, derivative of 0 is just going to be 0. So notice we have 2t times 0 is 0, and then we have plus 0, and so that's just going to be the integral of 0, and the integral of 0 is just going to be 0. So we can see that the integral along the first line segment is 0. So now let's go ahead and try to find the parametric equations for the second line segment. So once again we're going to use the formula where r of t is going to equal 1 minus t times r naught, and r naught is going to be the initial point in component form. So we have 2, 0, plus t times r sub 1, which is going to be the terminal or the end point in component form, so 3, 2. So let's go ahead and distribute over the 1 minus t. So we get r of t equals, now we get 2 times 1 minus t, which is just going to be 2 minus 2t, comma, well 0 times 1 minus t is just 0, and then plus, let's go ahead and distribute over the t, so then we get 3t and then comma 2t. So if I go ahead and add those two vectors together, we'll get r of t equals, now 2 minus 2t plus 3t is going to be 2 plus t, comma, 0 plus 2t is just going to be 2t. So we have 2 plus t, comma, 2t. So our x equation is going to be the x component, which is 2 plus t, and then the y equation, or the parametric equation for y, is going to be the y component, or just simply 2t. And once again, we did use the original formula, so we can say that the t-bounds go from 0 to 1. So now let's go ahead and find the integral for line segment 2. So the integral along C2, now x is once again going to be equal to 2 plus t. So we have 2 plus t times y, now y is going to be equal to 2t, and then plus x times y, and then times dx. So then if x is equal to 2 plus t, then dx is just going to be equal to the derivative for 1, and and then plus, now we have x minus y, so x is going to be 2 plus t minus y, which is going to be 2t, and then multiply by dy, so the derivative of the y equation is going to be 2. And don't forget we do need dt on the outside, because we're going to integrate with respect to t. So if I go ahead and simplify the integral along C2, or the second line segment, we have 2t times 1, which is 2t, and if I distribute that over to 2 plus t, we'll get 2t times 2, which is 4t, and then plus 2t times t, which is 2t squared, and then plus, we have 2 plus t minus 2t, which is going to be 2 minus t, and then times 2. So then if I simplify further, we get the integral along C2 of 4t plus 2t squared, and if I distribute over the 2, we get plus 4 minus 2t dt. And since the bounds are from, or the t bounds are from 0 to 1, I can go ahead and replace, or erase the C2, and say that we're integrating from the t bounds of 0 to 1. And so to simplify one more time here, the integral from 0 to 1 of 4t minus 2t is positive 2t. We have plus 2t squared, and then plus 4 dt. So now when I evaluate here, or when I integrate, integral of 2t is going to be t squared, plus integral of 2t squared is going to be 2t cubed over 3, and then plus the integral of 4 with respect to t is just going to be 4t. So let's go ahead and evaluate that from the t bounds of 0 to 1. So when I plug in 1, I'll get 1 squared, which is 1, plus 2/3, and then plus 4, minus, when I plug in 0, I'll just get 0. So that will cancel, and so I can rewrite 1 as 3 over 3. We have plus 2 over 3, and I can rewrite 4 to get the common denominator of 3 as 12 over 3. So we have 3 plus 2 is 5, 5 plus 12 is 17, so we're going to get 17 over 3 as the final answer. So now for number 5, we have the integral along C of x times y cubed ds, and then C is described by the parametric equations. This time we have 3 variables, x, y, and z, so x equals 4 sine t, y equals 4 cosine t, z equals 3t, and the t bounds are from 0 to pi over 2. So since we have ds and we're given specific parametric equations, we can go back to the very first equation that we used in this video, or the very first formula, where we can take the integral. Now the t bounds once again are from 0 to pi over 2, and we're going to replace everything under the integral with the parametric equations. So x is going to be equal to 4 sine t, so we have 4 sine t times y cubed, so y is going to be 4 cosine t. 4 cosine t cubed is going to be 64 cosine cubed of t, and then we have times ds. So we have the square root of x prime of t. So if x is 4 sine t, then x prime is going to be 4 cosine t. So if we take x prime squared, that's 16 cosine squared of t, plus y prime of t squared. So if y is 4 cosine t, y prime is negative 4 sine of t. If we square that value, we get 16 sine squared of t. Since we do have an extra z parametric equation in terms of z, we have to add plus z prime squared as well. So if z is 3t, z prime is going to be equal to 3. So then z prime squared or 3 squared is going to be a positive 9. And then we can multiply by the dt at the end. Now, like we did earlier, 16 cosine squared plus 16 sine squared. If you factor out the 16, we just get 16 times cosine squared plus sine squared, which is 1. So then 1 times 16 is 16. So then we get 16 plus 9, which is 25, and the square root of 25 is 5. So we're left with the integral from 0 to pi over 2 of 4 times sine of t times 64 cosine cubed of t times, we simplified the entire thing down to 5, and then we have dt. Now 4 times 64 times 5, if I use my calculator, is going to be 1280. That's a constant, so I can take that outside the integral. So 1280 times the integral from 0 to pi over 2 of sine of t times cosine cubed of t dt. Now in order to evaluate this, we can use u substitution, so I'll set u equal to cosine of t, so then du is going to be negative sine of t dt, so then dt is going to be equal to du over negative sine t. If I go ahead and substitute everything back in, we get 1280 times the integral from 0 to pi over 2 of sine of t times u cubed, since we set u equal to cosine of t, times dt, which is going to be du over negative sine t. Realize the signs will cancel. A negative can come outside the integral as a constant, So we have negative 1280 times the integral from 0 to pi over 2 of u cubed du. Now the integral of u cubed is obviously just u to the 4th over 4, and so we can substitute back into u, and don't forget we do have a constant, so we have negative 1280 times cosine of t to the 4th over 4. Now we'll go ahead and group these two together. So 1280 over 4 will be equal to 320, so we have negative 320 times cosine of t to the 4th power. So now we can evaluate from the t bounds of 0 to pi over 2. So when I plug in pi over 2, we'll get negative 320 times cosine of pi over 2 is going to be 0, 0 to the 4th is 0, minus cosine of 0 is going to be 1, 1 to the 4th is 1. So basically we have negative 1 times negative 320, so the negatives will cancel, and so we're left with the final answer of 320. So now for number 6, we have the integral along c of x times e to the yz ds, and c is going to be the line segment from 0, 0, 0 to 1, 2, 3. This time we do have only one line segment, so we don't have to break it up into two different integrals. So the first step is obviously to find those parametric equations for this line segment. So we're going to start by using the formula r of t is going to equal to 1 minus t, once again times r sub naught. R sub naught is going to be the initial point, so the initial point is 0, 0, 0. We're going to put that in component form, so 0, 0, 0, plus t times r sub 1, which is the end point or the terminal point, in component form, which is 1, 2, 3. So if I go ahead and simplify, if I distribute 1 minus t to this vector, it's just going to be 0, 0, 0 all the way. And then plus, if I distribute the t, we'll get t, 2t, 3t. So if I go ahead and add these two vectors, we're just simply going to get t, 2t, 3t. So we can say that the x parametric equation is going to be equal to t, the y is the y component of 2t, and the z is the z component of 3t. And once again, because we used the formula to find the vector function r of t, our t bounds are from 0 to 1. So now let's go ahead and rewrite the integral. So we have the integral, this time t bounds once again 0 to 1 of x, which is equal to t, times e raised to the power of y times z. So we have 2t times 3t, which is 6t squared. And then we have times ds, which is going to be the square root of x prime of t squared. So if x is equal to t, x prime is 1, so 1 squared is 1, plus y prime, which is going to be 2, 2 squared is 4, plus z prime, that's going to be 3, so 3 squared is 9. And then we have dt on the outside. So 9 plus 4 is 13, 13 plus 1 is 14, so the square root of 14 is a constant that can come outside the integral. So then I will rewrite it as the square root of 14 times the integral from 0 to 1 of t times e to the 6t squared dt. Now in order to evaluate this, we can just use u substitution. So if u equals 6t squared, du is going to be equal to 12t dt. So then dt is going to be equal to du over 12t. Now if I go ahead and plug that in for dt, we get the square root of 14 times the integral from 0 to 1 of t times e to the u, because I replaced u with 6t squared, and then times dt, which is du over 12t. Realize that t's will cancel. 1 over 12 can come outside the integral as a constant. So we get the square root of 14 over 12 times the integral from 0 to 1 of e to the u du. Integral of e to the u is e to the u. So we have square root of 14 over 12 times e to the u. Once again, u is equal to 6t squared. So e to the 6t squared. Let's go ahead and evaluate that from the t bounds of 0 to 1. So when I evaluate and plug in 1 for t, we'll get e to the 6 times 1 squared, which is 6, minus, when I plug in 0 for t, we'll just get e to the 0, which is 1. So that's going to be the final answer. Now, sometimes you might be asked to find the integral along c of the dot product of the vector field f, which we talked about in the previous video, and dr, or the derivative of the vector function r of t. And so the formula that we can use to evaluate this integral is going to be equal to the integral from a to b, and a to b are obviously going to be in terms of t, of the dot product of f of r of t and r prime of t dt. And so for f of r of t, and now f is going to be a vector which has its components. R of t is also going to be another vector which has its components. So we're going to take the components of r of t and sub them into f to find f of r of t. So let's go ahead and evaluate the line integral along c of the dot product of f and dr, where c is given by the vector function r of t. So for number 1, we have f of x, y, z equals sine of x times I plus cosine y times j plus xz times k. And so the vector function r of t is going to be t cubed times I minus t squared j and then plus tk. The t bounds range from 0 to 1. So the very first thing I'm going to do is go ahead and write each of these in component form. So for the vector field f, in component form, we'll just write it as sine of x, comma, cosine y, and then comma, x times z. And then for r of t, the vector function in component form, I'll write it as the x component being t cubed, the y component being negative t squared, and the z component being just t. So once again, what we need to do is find the integral from a to b of f of r of t. We need to take the dot product of that and r prime of t dt. So in order to find f of r of t, we need to plug in the vector function into the vector field. So the x component is t cubed, so I'm going to plug that in everywhere that has x. So we have sine of x and x times z. So we have f of r of t is going to be equal to sine of t cubed, comma, cosine of y. Now y is going to be equal to the y component, negative t squared, so we have cosine of negative t squared, comma, we have x times z. So the x component times the z component is just going to be t to the fourth. And so we also need to find r prime of t. Now if r of t is t cubed negative t squared t, then r prime of t, or the derivative of the vector function, is going to be derivative of t cubed is 3t squared, derivative of negative t squared is negative 2t, and derivative of t is going to be 1. So once again, the formula states we need to take the dot product of f of r of t and r prime of t. So when we take the dot product, remember we're going to multiply similar components together. So the x components will multiply together, get 3t squared times sine of t cubed, plus we multiply the y components together. So we have negative 2t times cosine of negative t squared. And then we can add the z components being multiplied together. So t to the 4th times 1 just gives us t to the 4th. And so we're going to go ahead and take the integral of that entire thing with respect to t. And then our t bounds are from 0 to 1, so that's going to be our a and our b. Now the integral of 3t squared sine of t cubed, we can go ahead and do u substitution. So I'll set u equal to t cubed. Then du is going to be 3t squared dt. And dt is going to be equal to du over 3t squared. Now if I go ahead and plug that back in, notice the 3t squareds will cancel. And so we'll have the integral of sine of u du. And the integral of sine of u is just negative cosine of u, and u is once again t cubed. So we have negative cosine of t cubed. Now for the integral of negative 2t cosine of negative t squared, I can do the same thing. U is equal to negative t squared. Then du is going to be negative 2t dt. So then dt is going to be equal to du over negative 2t. When I go ahead and plug that back in, the negative 2t's will cancel. And so we're left with the integral of cosine of u du. Integral of cosine u is positive sine of u, and u is once again going to be negative t squared. So sine of negative t squared. And then we have plus the integral of t to the 4th, which is just t to the 5th over 5. And then we can evaluate from the t bounds of 0 to 1. So when I go ahead and plug in 1 for t, we'll get negative cosine of 1 squared, which is just 1. Then plus sine of negative, well, we have 1 squared 1, so then sine of negative 1. And then plus 1 to the 5th over 5, just 1 to the 5th. Minus, when I plug in 0, we get negative cosine of 0 plus sine of 0. And then we have plus 0 to the 5th over 5, which is 0. So that will cancel. Sine of 0 is also 0. That will cancel. And so we have negative cosine of 1 plus sine of negative 1 plus 1 over 5. Cosine of 0 is 1, so then we have basically negative 1. So minus a negative 1 will mean plus 1. So 1 over 5 plus 1, which can be written as 5 over 5, is going to be 6 over 5. Alright, 6 over 5. We have minus cosine of 1 and then plus sine of negative 1. Now remember, sine of negative x is the same thing as saying negative sine of x. So we can rewrite it and put the final answer as 6 over 5 minus cosine of 1 and then minus sine of 1. Now, one of the main applications of the integral that we just looked at, or the formula that we just looked at, is going to be calculating work. So given a vector field f and a vector function r of t, we can go ahead and calculate work using the exact same formula. And so for this next problem, let's go ahead and find the work done by the force field f of x, y, z equals in component form y plus z, x plus z, and x plus y on a particle that moves along the line segment from 1, 0, 0 to 3, 4, 2. So realize that we already have a vector field here, but we need to find a vector function r of t. So once again, we do have a line segment that connects 2 points, so we can use the formula r of t is going to equal 1 minus t times the initial point is 1, 0, 0, so written as a vector, it's just going to be 1, 0, 0, plus t times the ending point or the terminal point, which is 3, 4, 2, written as a component form, just 3, 4, 2. Once again, because we use this formula, the t values range from 0 to 1. And so if I go ahead and distribute 1 minus t into the vector 1, 0, 0, we get 1 minus t, comma, 0, comma, 0, plus, if I distribute the t over to 3, 4, 2, we get 3t, comma, 4t, comma, 2t. Now if I go ahead and add those two vectors, we add similar components. So 1 minus t plus 3t is going to be 1 plus 2t. 0 plus 4t is 4t, and 0 plus 2t is 2t. So that is going to be the vector function r of t in component form. So now let's go ahead and find f of r of t. So once again, we're going to plug in the components of r of t, or the components of the vector function, into the vector field f. So f has y plus z. So the y component of r of t is just going to be 4t. So we're going to take 4t plus z, so the z component of r of t is 2t. So 4t plus 2t. I'm going to rewrite that as 6t. So we have 6t, comma. Now, next one is going to be x plus z. So the x component of r of t is 1 plus 2t, plus z. So the z component of r of t is 2t. So I'll rewrite that as 1 plus 4t. I can rewrite that 1 plus 4t, comma. Now finally we have x plus y. So x is going to be 1 plus 2t, and then y is going to be plus 4t. So then I can go ahead and rewrite it as 1 plus 6t. Now remember, we need to find r prime of t now. So we're just going to take the derivative of the vector function. So the derivative of 1 plus 2t is just going to be 2. Derivative of 4t is 4. Derivative of 2t is 2. So once again, we're going to take the integral from a to b of the dot product of f of r of t and r prime of t dt. So if we take the dot product of these two, we're going to multiply similar components. So 6t times 2 is going to be 12t, plus we're going to multiply the y components together. So 1 plus 4t times 4 is going to be 4 plus 16t, plus we go ahead and multiply the z components together. So then we get 2 plus 12t. Now if I go ahead and simplify that, 12t plus 12t is 24t, 24t plus 16t is going to be 40t. So we get 40t plus 4 plus 2 is just going to be 6. So we're going to take the integral of 40t plus 6 with respect to t, and then from the bounds a to b, which in this case the t bounds are from 0 to 1. Now the integral of 40t is going to be 20t squared, and plus the integral of 6, which is 6t. So let's go ahead and evaluate from the t bounds of 0 to 1. So when I plug in 1 for t, we'll get 20 times 1 squared, which is 20, plus 6, minus, when I plug in 0, we'll just get 0. That cancels, and so our final answer is going to be 26.